Let me introduce to Dr. Roula Bachour. Sorry if I don't pronounce it well.
Yes, no worries.
Okay, that's the Director of Customer Success at Hydrosat. Dr. Bachour is an agricultural engineer and irrigation specialist with more than 15 years of international experience in remote sensing, water management, and digital agriculture. She holds a PhD in irrigation engineering from Utah State University and has worked on projects with organizations such as the World Bank and NASA. And through her career, she has focused on using Earth observation and satellite technologies to improve irrigation management, agricultural productivity, and the sustainable use of water resources. At Hydrosat, she works closely with farmers, agribusiness, and water managers to transform satellite data into practical tools for decision making. And we think that for SUSTAGRI students, her experience offers an excellent example of how advanced technologies such as remote sensing, data analytics, and digital twins can be applied to address real-world challenges in sustainable agriculture. So please join me in giving a warm welcome to Dr. Roula. So please, thank you very much for joining us today, and you can start whenever you want.
Yeah, thank you so much, Javier. I think, well, that's very nice of you with the introduction, so thank you. And yeah, I'm really happy to be here today to talk to you because well, I will say not so long ago, but some time ago I was in your seats where I was doing my master's and then PhD and studies, and I did also want to see what's next. How can we use this knowledge that we are learning practically? You know, like I don't want just textbooks. I wanted to know more. How can we use all these theories and things that we learn about, what we read in the books? How can we practically make use of this? So hopefully, with the story I will tell you here, you get a bit of inspiration and see how some of the remote sensing and GIS data can be used in this case for irrigation and agricultural water management. So yeah, that's the title of my presentation is about looking into the root zone through the leaves, and I will tell you how we do that using thermal remote sensing. So let me start first by telling you about Hydrosat. And I did decide to start with this image or a short video, actually, and an image from the launch of one of our satellites, because what this one captures is more what is known about Hydrosat. So people know that we are a satellite company, that we build and operate satellites. However, our mission is not just simply to put satellites in orbit. So it's not about putting sensors out there. It's more about using thermal information into and transform it into actionable intelligence for water management, for food security, and other applications. And this is actually why the founders of Hydrosat started the company. So it was really to help the Earth manage its most valuable resource, which is water. Okay, and in this short video I will play here, you will see the different countries. The size of the bubble is the different countries with their population growth. And this is a short video going from the 1960 into 2020, seeing how the water per capita is decreasing, okay? And this is where we have our stress line, and then you could see now, and now I guess we are even lower, many of the countries are passing this water stress line. And it is one of the biggest threats to food security, along with, you know, the whole climate change, the whole population growth, etc. So managing water is an important thing we wanted to tackle, and agriculture is one of those most users of water. So that is why the focus is on managing water for agriculture. And this is how the company started. And sorry, I need to move to next slide. And because of the of the use of satellites, we want to transform, this knowledge that we have from satellites into actions about better managing water for irrigation. So that's the story I will tell you about how we use that, how we do that with our thermal data. So first, to start with, why the thermal data? What's the advantage? Do we really need it? Yes or no? Because you hear about satellites. You have, this is the spectrum, electromagnetic signals, the different bands of the spectrum where you have seen imagery. So you have the visible, you have the near infrared, you have the short wave, the long wave, and the radar data, the microwave data. So you have a whole spectrum of light and satellite available data. And our focus is really about the long wave infrared. And that's we are building the satellites around these capabilities. And it's more to uncover these hidden signals. And especially when it comes to the agriculture and looking more into calculating the water consumption, the evapotranspiration, which is how much water the plants are taking from the soil, and then how is this transforming into production and yield, and how can we better optimize this water productivity. So it is really about this getting early enough information weeks before about the crop water stress, about maximizing water productivity and avoiding losses and waste of water. Okay, so this is really our competitive advantage, if I want to put it in commercial point of view. And yeah, so that's how we do it. But maybe since we are talking about a seminar about master's program, so let me give you a lecture about irrigation and crops. I don't know. I know that you guys have different backgrounds and different experiences. So maybe I thought it's good to give you a quick overview about how is irrigation management happening. What do we look at as irrigation engineers, and how do we tackle the problem historically, classic ways, and how has the innovations and science moved across the time. So bear with me with some technical maybe explanation. And this is all about, when we talk about water for irrigation and plant and irrigating plants, it's all about this transport of water and this continuum that we talk about. So it's what we call the soil, plant, atmosphere continuum. Okay, so this is the water flowing through the plant. And some people say the plants are just these channels of, it just transports the water from the soil into the atmosphere, from high water potential to low water potential. And these flows of water, they go through the inside the cells of the plants, and these are what we call the xylem, or if you remember your fifth grade biology course is about these transport or channels within the plant's cells. Okay, and this uptake is driven by an atmospheric demand. So there is some heat, and then the moisture is in the soil. It goes through the plant and evaporates. Okay, and to better manage this irrigation and this water, it's really all about the soil. Is there enough water in the soil to go through the plant and transpire and form the photosynthesis and the whole plant material? And to measure and know if there is any moisture in the soil, people generally used sensors. So this was always the approach. You put a tensiometer in the soil, you measure the soil water potential. But it doesn't matter where you are measuring. So whether you measure things in the soil, or you come to the trunk and then put a dendrometer, or measure the leaf water potential, or you measure the atmospheric demand. So wherever you are through that continuum, it's the same representation. So you are measuring this flow. And it is good enough to give you an indication of what's happening, and then you can better manage it. However, these sensors and devices that you put, no matter where in the plant, whether in the soil, whether on the plant leaf, and so on, have a lot of challenges. First is this local representation. So it's really a point measurement. So if you put a tensiometer in the soil, it's really measuring a tennis ball size only. And then that's really small to decide and generalize. This is a screenshot of a soil moisture map from our platform. And you have a lot of variability within the soil. So if you want to place a tensiometer in this 2-hectare field, if you put it in this zone where its moisture is very high, you're always going to overestimate the moisture, and then you end up stressing a big part of your field. The other way around, if you place your tensiometer in that part of the field, then you're going to end up always saying it's stressed, stressed, stressed. So you're going to irrigate, and that means you're going to waste a lot of water and damage the crop in the areas that have higher moisture. So sensors are good. They measure if they are well installed and calibrated, etc., but they don't give you the full picture. That is why the remote sensing comes into the picture and helps this. So, and people soon enough started realizing, okay, you know, sensors, too many sensors everywhere is not something manageable at a large scale, and we have to find something else. You could also break them if you walk with the machine or if you drive with the machinery above you. There are many challenges for these ones. When I studied agriculture and irrigation, they taught me that my best or my Bible back then was this FAO 56 book about crop water requirement. How do we calculate evapotranspiration? And this was our best guess for knowing how much the crop wants water. So what was this methodology? It says that you need a weather station, and this weather station from the climatic data, you get what we call a reference evapotranspiration, which is the water demand for a reference crop, that is grass in that case. And then for each crop, they built these crop coefficients tables or graphs that you see here. And then depending on the period of the growing season, you can use a different coefficient to convert this reference ET into a crop evapotranspiration. And which was and still is used by many, many, many irrigators everywhere around the world to kind of have a standard method of doing it. What are the problems of these methods? So 2 challenges. One is that in that book, they describe the conditions for these weather stations. So they make some assumption about surface bulk resistance and so on. And these conditions are that the station should be placed on a grass field of at least 40 meter by 40 meter fetch, with a clipped at 12 centimeter throughout the season and well irrigated. Practically, I've never seen a weather station in such conditions except in research institutes. So when we come to real life practice, most of the cases a station from one of our farms, and it's just like somewhere between 3 pivots in the field. So it's just like really in this dry area outside of the way, and it's not really representative of the conditions of the field. And in most of the case, you have this advection and movement of the air that tends to overestimate this reference ET. So you're starting with a reference ET that's overestimated or not really representing the reality. On the other hand, these crop coefficients were really developed in the 80s using some lysimeters back in Idaho, and the varieties of wheat and maize and rice that were back then existing are completely different than these days. You have all these drought resistance varieties now, or adaptability and so on, high productivity. So all this is not really captured with the standard coefficients. So this started making this like, okay, I want to manage better my irrigation. It's becoming more precious to have more precision irrigation and so on. So what do we do? And this was also along with the start of remote sensing. So one of the things that people started doing is saying, okay, how about, because now we have these satellites and they can measure the near infrared and reflectances of these crops. So we can measure the NDVI. We can know how the crop is growing and not really these standard curves. So instead of going into these strict lines and so on, we can actually find a relationship between this crop coefficient and the NDVI and build some, adapted crop coefficients. And it was applied. And while it is an improvement from the standard curves, however, this approach still misses the dynamics and the reality of what happens in practice. Because when you have different irrigation events, so even what you see sometimes from above, it can hide what's happening in the root zone. So you don't see what's happening in the root zone. You don't know if there is enough available water or not. So the height of the crop and the greenery of the crop is not always the full story. This is just some graph from a real measurement using lysimeter about what is the standard coefficient of crop coefficient and what was it in reality for different irrigation regimes. So each farmer was using a different irrigation system or different amount of irrigation, different source of water, if there's water treated water or not, has salinity or not, and you could see it all over the place. So if you were having some kind of a drought stress and then you are still using the reference curve, what you're going to do is you're going to end up over irrigating because you overestimate the demand. On the other hand, in some pristine conditions, when you have high water demand, etc., so the coefficient can be high, the plant can produce a lot more. However, you are limited because you're under irrigating. So you have all these conditions of over irrigation, under irrigation, because you're not seeing what's happening in the root zone. Okay, and this is where we come to tell you the story that green fields often they hide if the crop is in crisis or not. And you probably have heard about, that, yes, but then we can look into the near infrared. We can see before our eyes can see it. This is a nice image, actually, I have from one of our satellites where you could see in the first one, this is over California, and then you could see this area with a lot of green fields. And if you look, and then while everything looks green, you think like, oh, nice, I can see everything is green and productive. When you dig deeper and look into the chlorophyll or this red edge and see what is happening into the plant nitrogen and chlorophyll and so on, you can see a lot of variability. So while here they are all green, here you could see some are really having lower chlorophyll. So it is damaged. You didn't see it with your eyes, but then your infrared saw it. However, the fact that the chlorophyll is damaged is already too late because you want to detect it before the damage has happened. So here already the problem is affecting your yield. You are too late. It's earlier than your eyes, but it is already too late. And this is where the thermal comes in to help you detect this stress way deeper, way earlier. And then I will explain how we do this by, immediately looking into the plant reaction to any kind of stress. And this is the whole concept and modeling behind or the science behind our model started with the founder of IRRI-Watch, the model we are using now, model called surface energy balance modeling for land surfaces, and his name is Wim Bastiaansen. So he started this about 30 years ago. The models are published, it's there, they have more than 22,000 citation. It is validated by thousands of people. I was one of those students who used the model in Utah in the US and then tried it and applied it. And then at some point, Wim decided to put this into the practice and help people to better manage irrigation. So what is this science behind it? So let me try to simplify it. It's all about an energy balance. So you have radiation that comes from the sun. This radiation can either heat the soil or evaporate the water. To evaporate the water from the plant, you need energy, or it can go also to heat the air mass above the crop, which is this heating factor, okay? And these are in balance. We can measure with the thermal satellites the heat, we can measure the radiation, but then we cannot measure the actual energy going into evapotranspiration. So we calculate it as a residual of this equation, okay? But then what does it mean? So if we take this equation and balance and apply it over a landscape, okay? And then here you put it over a fallow field. So you have radiation coming from the sun, part of it seeps into the ground, and very little goes into evapotranspiration because there's no water to evaporate. So most of the energy goes into heating. And that's why if you walk outside in summer and over a bare soil, you feel heat coming into your face. So you feel the heat of energy. If you, on the other hand, walk over a well-irrigated planted field, you feel So this is the same radiation coming in, seeping a bit into heating the soil, and most of this energy is used to evaporate the water. So the plant is using this energy to evaporate the water, and hence very little is left to heat the air mass above the crop. And that's how you have colder temperature over these vegetated surfaces that are fully transpiring. And then these are the two extremes of this temperature. So when we look from the satellite and we measure temperature across any landscape, then you are really between these two extremes of very low, zero almost evapotranspiration, and very high ET, which is the maximum potential of that location. And that's how you can see everything in between is calculated. And by detecting these different temperatures, we can also tell what is happening into the root zone. Why? So if we think about the plant, I don't know if you've had these experiences where you go on vacation, you forget your plants to irrigate your plants, and you come back and you see these leaves turning a little bit. And that's because what they do is they close the stomata. So the plants, they have at the leaf level, they have these cell guards and stomata. So they open and close to let the water out and let the carbon in. So these openings, they are in direct communication with the roots. So we always say about this continuum. So they are in direct communication with the roots. And the moment they detect that there is water shortage in the soil, then they're going to shut down. So they start resisting this flow of water. And if you are a stomata or a leaf closing all the pores to avoid water evaporation, but you are still hit by the same radiation, then the temperature of that leaf is going to increase. So we are increasing the temperature, and that is why we can detect immediately. So it's an immediate reaction through the plant. Within an hour, you know that there is no water in the soil, and then I'm shutting down, the temperature rises. And by measuring the temperature, we can tell if there are any places with any water stress. And that's why what we infer from this temperature calculation and the transpiration process is this stomata resistance, and hence what we call the soil water potential. So as if every leaf you are putting out there is a virtual tensiometer. So it's like a virtual tensiometer placing everywhere in the field, and it is measuring the suction power that the plant is doing to extract the water. And this is your indication. So you use kind of what we call the water retention curve to move this soil water potential into soil moisture. And this is a soil moisture here on the pixel level that we have from screenshot from our portal, but it also translates into a moisture status. So what does it mean for a farmer looking into this? Is this 19% moisture, is it good or is it bad? Do I need to irrigate? What do I do? And so on. And this is how we translate this more into a moisture status, like a traffic light indicator, green, red, blue. And then you know that, okay, the moment your fields are starting to turn into orange, you need to irrigate. And that's how we look into the moisture status and look at the forecast of the weather, and we can provide irrigation advisory for these farmers. So that's usually how this is happening. And this has been applied in over 60 countries. Currently, this morning, we sent data to about 67 different countries for clients all over the world who have more than 120 different crops that they are planting. And it is a fact that these clients are coming and choosing us for several reasons. One is because we have daily data, and farmers need to take decisions on a daily basis. So you need to take also decisions that are quick. You need to have actionable decision early enough. So you need early warning, basically. And that's why the thermal can help us to identify the stress early enough. It is a proven science. It's a lot of validation out there, and then testing and then comparison that people have published or shown, or our clients are seeing themselves. And it's also, you get these insights that are helping you to better manage the water and eventually improve your yields. And in addition, we can go global. So we have the whole globe we can cover, and we have the technical support that we provide to our clients, and that's why they come to us. So the solutions, when we talk about our solutions, so we have different levels of our solution all around for crop and water solutions. It is about the crop health, identification of stress. It's about irrigation and water use. How do we do irrigation planning? But also how do we track water use? Like how much people have used? Did somebody illegally use the amount of water they should not have? And so on. How do we optimize this resource? Where do we irrigate first? Where is the water needed and how much is needed? But also the solutions are for policy or regional insight. So the level of our data is also from field level to regional level. And since we are talking about root zone and soil moisture and irrigation planning, I will just focus on what we call our IrriWatch product, which is field level IrriWatch product. And this is more about irrigation planning. So these are some screenshots from the portal that we have. And it's about this traceability of soil moisture day by day. You can know what is the average moisture in your field, what is the planned, what is a recommended irrigation planning that you have to do. You have insights into the crop growth. You get alerts also if the crop is having any production problems and so on. And also it makes it simple when you have it, farmers in the field, they have their mobile phone, they walk in, and then we have this mobile app where they can go check the stress, the alert regions, and then take scouting notes, and then have also real experience from putting the remote sensing imagery on your phone in the field and then seeing what is it happening there. All this data, so we have different type of application and clients. We also provide the kind of more than 120 different layers that around the water, irrigation, and crop. We provide them via API because we have some clients all over the world that want to take their own, they make their own application, their own language, simplify it or make it more complex, whatever that is. And we have these capabilities also to do this in APIs. I'm going to move quickly into maybe 3 stories from some of our clients, just to put it more realistic, also for you to understand how people are using IrriWatch data and the data from Hydrosat. This is an example from California in Madera County. So this is a client for Hydrosat for the last 6 years. And for them, what happens is, I don't know if you know anything about California, there was a lot of drought. There was, in 2014, a SIGMA Act, Sustainable Groundwater Management Act, that was passed to manage the level of groundwater and try to control more the water rights and see how much people are using. And while flow meters were one of the methods of using, metering how much people are using, they realized soon enough that these are not always accurate. They can be manipulated. People can bypass this flow meter and overuse water. So what we have been doing with them is monitoring the real water consumption from the crop. And we compare this to the allocation. So in each sub-basin, they have different amount of water allocated, and the farmer from day to day, they can track how much water they are using. And based on this, they also take decisions. So if they see they're going to exceed the allocation and they're going to get penalty at the end of the day, then what they do is they limit or they put some lands into fallow, or they start trading water across the basin. And then that's how they're reaching a more sustainable water level in this basin in California. Another example, this is more from India, about rice production, where rice is really a big crop, a big water user crop, because most of the rice is really grown by flooding. And when you flood rice fields, from one side, you overuse water, you have high evaporation, but you also emit a lot of methane into the atmosphere. So what companies like Bayer is doing here in this case is moving into some varieties of rice that can be direct seeded, and they can tolerate what we call alternate wet and drying. And with this one, they can trace how much, or like you can save a lot of water and reduce methane emission, which is one of their objective or target, to improve water productivity, reduce emissions. And that is what we are helping them with, to monitor these new fields with these new practices. Same we do for regenerative agriculture and so on, and compare to some baselines, what was the water consumption and how it is getting better now. Okay, so this is more from like kind of a target of climate and emissions and water savings. More from a farmer point of view, this is an example from Egypt, where farmers have been using our IrriWatch app to go and see and decide on their irrigation management. There's a lot of water shortages also in Egypt, and one of the traditional crops that was really planted a lot is this sugar cane that consumes a lot of water. There's a big move towards sugar beet, which consumes less water, but people don't know how to manage it, how to irrigate it. And we have seen for several years now, we are working in Egypt with those farmers, and the water that is being used in irrigation is reduced up to 40%, with like a little bit of more than 15% increase of yields that they are having there. So and this is we are seeing across different examples. So I tried to put different examples from different places across the world, and thought maybe to trigger the discussion here. And that's it from my side. So yeah, thank you.